Hello everybody and welcome to the webinar on PD monitoring in Rotary Machines. Today your host will be engineer Lorenzo Paschini, who will be sharing with you some of the knowledge obtained in his many years as a service engineer working for Techimp-Altanova. Also, you can all send your questions in the questions section. I will be there trying to answer some of them. My name is Andrej Šepčić and I will be moderating the webinar. We will have some interesting questions for you during the webinar. It will be only 1 hour long, so we will not take too much of your time. So without any further ado, Lorenzo, take it away.
Thank you, Andrej, and welcome to the Introduction to Partial Discharge Diagnostic and Rotating Machines webinar. I'm Lorenzo Paschini, senior service engineer at Techimp-Altanova Group company, a company based in Italy, but present worldwide. That's what we're going to, let's say, speak about today. We will start speaking about generic partial discharge and rotating machine topics. We will then go into the PD sensors for rotating machines. We will see the differences between online test versus offline test for PD measurements. We will give a brief overview of what are the typical PD phenomena. We will see one of the main topics in this kind of job, that is denoising the signal and identify crosstalks. Then we will go through PD analysis. And finally, we will present a short list of Techimp products and services for rotating machine PD test. Let's start with some definition.
Lorenzo,
yes?
Excuse me, just a second. Are you sure you shared the screen? Because I don't think we see it. We still see the basic one, Introduction to Partial Discharge Diagnostics on Rotating Machines.
Sorry, yeah, you're right.
Okay.
Sorry, guys, let's go.
Just one
back to the presentation, yes. So the definition that we have for partial discharge that is suggested from EAC. It's a localized electrical discharge that only partially bridges the insulation between conductors and which can or cannot occur adjacent to a conductor. Similar definition is given from the IEEE. And basically what we need to know from partial discharge is that is a effect due to a defect in the insulation that is activated by electrical stress, voltage stress. How do we study the PD phenomena? We study PD phenomena through the phase-resolved partial discharge pattern, normally known as PRPD pattern, where we save all the information of thousands of PD pulses recorded for each second, and we plot them correlated with the phase angle. On the top here, we have an historic Lissajous visualization of partial discharge, and on the bottom, a more modern visualization of partial discharge. We can have on the vertical axis the PD pulse amplitude, while on the horizontal axis we have the phase angle when the PD occurs. We can have in literature some guides and standards for rotating machine testings. We have, for example, the EAC 634-27 Part 2 related to online partial discharge measurement. We have the IEEE 1434, and we have also the CGRE 258 application of online PD test to rotating machines. What can we say about the sensor to record partial discharge in rotating machine? We will see how we detect the signal. We will see what are the sensor's typologies, the requirements of such sensor, and the positioning of the sensor. In the end, signal and safety. How do we detect the signal? Basically, PD phenomena generates signals that are sources of high-frequency electromagnetic signals and irradiated signals as well. So we can let's say, force the conducted signal to pass across our sensor, or we can try to measure this sensor with an antenna or something different. Different sensor will always give us different output, different sensitivity, and they can provide or not the synchronization signal. Most popular sensors are the capacitive couplers. Those are connected normally to the rotating machine connection, and the signal is measured or across measuring impedance as a voltage drop, or with an high frequency current transformer. In the end, there is also another solution that is with antenna sensor. Those have to be installed into the stator, and they will pick up the irradiated signals. Obviously, 3 different sensors will give us different parameters, different capabilities. If we start about the sensitivity, the capacitive sensor that picks up a conducted signal is characterized by the very high sensitivity, while the capacitive sensor with an HFCT has a lower quality signal information, while the antennas, they have a very good sensitivity locally, but we need, let's say, many of them to have a proper coverage of the stator windings. The installation of the sensor in capacitive and capacitive with HFCT sensor, it's a medium effort, while with to install antennas, it's a very high effort because we have to install something inside our stator. The safety characterized by the different sensor is medium for the capacitive because we always have a conducted signal going to the acquisition unit. When we have a capacitive with HFCT sensor, it's very high safety because the signal is inducted, and with the antenna, the safety is high as well because it's an irradiated signal. One very important topic from my point of view as a testing engineer is the synchronization signal presence. As I told you in the first slide, we build the PD data in PRPD pattern, phase resolve PD pattern. In order to have the phase resolution, we need to have a synchronization signal that is a voltage signal directly correlated to the applied voltage to the insulation. This signal is made available with the capacitive couplers, but we don't have such signal when we have sensor with the capacitive coupler plus an HFCT or antennas. The coupling principle is a conducted signal for capacitive sensor, inducted signal for capacitive sensor with an high frequency current transformer, and radiated signal with antennas. Quickly, it's time for the first quiz that will be introduced by Andrei about the PD sensor.
So guys, now you heard how we decide what would be the best sensor for rotary machines. And we're going to ask you a question. What did you understand? What is the preferred sensor for testing partial discharge on rotary machines? So what is the preferred sensor? Obviously, you can do it with any of these, but there is one which we would prefer because if you look at all the aspects which Lorenzo presented, so if you look at the sensitivity, installation, safety, sync signal, coupling principle altogether, which one is according to you the best? So I already see that 92% of you guys have given a correct answer, so I see that you understand. I'll repeat that
alert from Google
you
Chrome.
can do this with
New subscriber.
any possible sensor, but one is preferred. So we have almost 50% of people voting, which is very good. I see you're attentive. I hope you like what Lorenzo is presenting, and we're going to close the polls in 5, 4, 3, 2, and 1. The polls are closed, and let's share the result. The answer was, of course, C, capacitive coupler, and you were paying attention. 88% of you said that is the preferred sensor for rotating machines. So this is it from me for now. Let's take it on.
Thank you, Andrei. Just to complete this question, this quiz, I would say that as per my experience as a service engineer, I've been detecting the signals with both these three families. But Techimp philosophy is oriented to the capacitive sensor with a measuring impedance. Now, let's see what are the sensor requirements. Since the permanent sensor will be installed in a very high, let's say, in a very critical environment, whenever we want to install the sensor, we must be sure that it's safe and it's not adding any risk of failure to our asset. So we have a very stressful type test. In the picture, there is a impulsive test layout for our sensor. Each sensor is subjected 3 times the rated voltage for a withstand test, and each sensor shall be free of partial discharge at the rated voltage after a pre-stress session. In this case, for example, we have even a higher level of safety. We also test our sensor and we mark them with the different, let's say, trademarks, A+, A++, in order to, let's say, have a very high voltage stress acceptable for the sensor. In the end, the capacitance and the voltage ratio shall be tested with the very small tolerance values. Now, sensor positioning. For the same reason, we install this sensor in a very, let's say, particular environment. And normally, we just install them once in a lifetime. We have to make sure everything is made properly. Our sensor shall not have magnetic parts. I mean, they shall not have magnetic parts. We should have a PD sensor that does not reduce the insulation capabilities of the stator and of the bus bar section. We should have sensors those are okay with the ongoing temperature and vibration stress. And in the end, very important, we should make a proper installation with proper spacing, avoiding corona and surface PD that would affect the PD measurement for the rotating machine. And we have discussed about the PD sensor installation. Now, obviously, we cannot accede directly to this PD sensor since they are in a very particular environment. The signals from the sensor shall be carried outside with proper conduit and trunks, and the signal shall be made available at an external derivation box. Our derivation box, they provide actually 2 things. One is the synchronization signal from one of the phases, and they introduce safety for the acquisition unit and the operator. There are some, let's say, voltage control in the derivation box in order to work in a very safe condition. This particular aspect is important practically to have the chance to make the test without special permits, without special working risk assessment, and giving us the chance to test the generator whenever we want without big problems. Now, let's give a quick look at online test versus offline test topic. First, we will present a typical PD offline test layout and with its characteristic, and a PD online test layout. Then we'll see a technical comparison, so the data quality of these 2 solutions, and a practical comparison. In offline PD test, we normally have an outage, so we have accessibility to the windings directly. We can install even temporary our capacitive coupler. We will inject the voltage in one of the coil, and we will measure one by one with a portable instrument. What are the technical aspects we have to keep in mind when choosing to do an offline test? The voltage stress here is phase to ground, and it's constant along the whole winding. We don't have any phase-to-phase stress, and we have the very same voltage stress applied to all the winding. While normally working condition, we have a, let's say, variable voltage stress along the winding. Then the generator or the motor is motionless, steady, and there are no temperature changes during the test. Let's say not significant temperature changes during the test. Also, we are not taking into account the mechanical behavior of the stator. We don't have vibration. And in this case, we have to keep in mind that one good thing is that if we can open the start point of the generator, we can test phase by phase. This gives us a chance to identify better the source and to have a more, let's say, clear comparison between the different phases. The voltage source shall be for sure free of any PD signal or high frequency signal in order to have a good measurement. One very practical aspect is that we can ramp up and down the voltage stress in order to evaluate PD inception voltage and PD exception voltage, very classical parameters normally used during testing, laboratory testing. Is it also possible to overstress the insulation? We don't have any limit to the voltage we apply. We can go over the rated voltage of the insulation and see what is the behavior of the electrical insulation system. Then we see something about the online PD test. I'm considering with online PD test a running generator with permanently installed sensor. Those are available from a derivation box and can be measured with a portable kit. The technical aspects to be taken into account is that in this case, the electrical stress is the routine stress of the winding, the same electrical stress that is always applied to the winding. We can take advantage in some cases, as the standard suggests us, to different load parameters and different temperature parameters for the PD analysis. On the negative side, since we are testing all the phases together and they are all connected to the same grounding systems, we can have signals from one phase flowing into the sensor of the other phases, giving us the so-called crosstalk effect. We shall take care during the analysis to identify properly these signals and to match each signal with its phase. With the online test, we may have very easily some external disturbances. Those may be related to the electronics of the generator, to the ongoing activities nearby, but everything is connected, so we can have this kind of disturbances. Another good thing that we can do with the online PD test is that we can perform simultaneously on the three phases the PD test, and we can take advantage of the different phase shift between the phases to make the analysis. In the end, one very good thing about online testing is that as a hypothesis, we have the permanent sensor installed. And that's a very key point because we will have the same sensitivity along the lifetime of the generator since we are using always the same sensors. Last but not least, the PD test can always be performed in a very safe condition. Now, let's make a short technical comparison. Permanent sensor required. In offline, we don't need them. We can bring our own sensor and install it temporarily. On the other case, in online, if we don't have any permanent sensor, the measurement will be impossible. We don't have any crosstalk effect in offline testing, while we have this kind of effect in online testing. But we don't have the real electrical stress during offline test. That's something that we, of course, have in online test. The correlation of the historic data, is it very easy to do with the online test because it only depends on the acquisition unit. If we are using the same acquisition unit, we will have the same readings. On the offline test, we may have different sensor, different acquisition unit, especially if this job is outsourced to third companies. 1 year we can have one company coming with the Techimp instrument and sensor. The other year, somebody else can come with another instrument, and the correlation can be hard to do. Continuity is a very key point when studying rotative machine data historically. The team stress is not present in offline tests. We only have electrical stress. Instead, in online tests, we have aging, we have thermal, we have mechanical stress, and so on. Under a very, let's say, low-level practical comparison, we can say that the offline test has a higher price. We need to bring more assets in the field to make the test. We need to make an outage, while during the online test, it's just about the service job. The customer effort for the offline test is high because we need an outage, we need support, we need to prepare risk assessment, and so on. On the online test, it was low, but I kept high, sorry for that, consider low. I will try to fix it before we send to you the presentation. Outage required for offline test obviously is yes, because we cannot put our hands there without outage. In online, we don't need any outage. PD sensor for offline tests are brought by service company. Instead, in online test, we need to have the sensor, and we also need to study the sensor compatibility between acquisition unit and sensor. On the safety point of view, the offline test is obviously more hazard. We introduce a new voltage generator. We are with open machine. It's not so safe. From the stress point of view, it's a particular discussion because with offline test we can apply different voltage level. While with the online test we will have only the electrical stress that is fixed, but we will have the normal cases of temperature and load changes stress. Operation the department shall be involved during offline test. Of course, yes, because we need outage and all these safety issues. With online test, it's very easy. We just need a simple permit to work. Material required when we go offline, we need the HV source, the sensor, the PD, the sensor for the PD, and the acquisition unit. In online testing, we only need the acquisition unit that will be connected to the sensor. Now it's time for the second question. Please, Andrei, go ahead.
So thank you, Lorenzo. Now we were speaking intensely about online and offline testing. So we would like to see if you understood exactly what we meant by online and offline testing. So what is the biggest difference regarding online and offline test? Is it A, online test is done continuously and offline is not? Or B, online is done with internet present and offline without internet, and online test is asset connected to the net, and offline is an asset or generator or rotary machine disconnected from the electrical network. So which one of these three? And before you answer, because I see that the things are going in a different direction, we have two ways how to observe, let's say, online and offline when we talk about PD. What Lorenzo was explaining was, of course, testing, like a spot test. We also have, let's say, this separation of online and offline when we talk about monitoring. So we can say online monitoring, but this is not online like here. So here, I see that most of you right now, I have almost 50% of the people voted in 1 minute. So we're going to close the polls. So let's close the polls and share the results. The correct answer is actually C. Online asset is connected to the net, and offline your asset or your generator is disconnected from the net. You are the one who is bringing the voltage. Where 60% said online test is done continuously and offline not. When it comes to the continuity, they are all done in the same way. You do them, let's say, for a few half an hour, 1 hour, 2 hours, and then you are done. But in this case, what we meant to say is that in an offline test and in an online test, there is no time difference in execution of the test, apart from the fact that you need to also mount the generator, which will generate the offline voltage. Anyway, okay, be careful and listen to what Lorenzo is saying, and let's see what else Lorenzo has got installed for us. Let's move on.
Thank you, Andrei. Next topic I expect to be one of the most interesting for you guys. It's a typical PD phenomenon identification. First, we will speak about the phase resolved PD pattern and the polarity. And then we will go into each single major PD phenomena we find normally in rotating machine. And we will see what are the characteristics of the pattern related to the phase resolved PD pattern related to each defect. First, PRPD pattern for us is the key, always. In the PRPD pattern, we normally put the pulse amplitude, the pulse polarity, and the phase angle. These information, they are, let's say, the only way we have to recall the physics of the phenomena. The applied voltage is the engine of the PD. If we don't have the applied voltage, we don't have the PD. And the correlation between both applied voltage and partial discharge phenomena is the one that will give us the tools to carry out the phenomena identification from the PRPD, phase resolved PD pattern. We start with the voids. Normally, generator, in motors, we have a system of insulation made with normally, recently at least, with mica. And even if we have a very strong, even if nowadays there is a very strong vacuuming during this process, we still have some voids present in the generator. These voids will have a very characteristic pattern with a symmetry between the positive and negative pulses. We will have a regular phase interval, and we will have a low magnitude at this stage, and also triangular shape. I forgot to mention it before, sorry for that, but I think I need to point out this thing. Rotative machines are designed not to be PD-free. They are designed with materials and technology to withstand partial discharge. So 9 out of 10, if we test one generator, we will always find some kind of partial discharge phenomena. It's pretty common. The important thing in this case is to identify such phenomena and check it along the time. So PD in a rotating machine is not as bad as PD in cables, for example. The insulation material in this case is designed to withstand such PD stress. Going on to the typical partial discharge phenomena, we have also embedded the lamination that we can say is a second stage from the microvoid. So we have the lamination that is inside the insulation, not on the boundary sides with the metallic part, but in the middle of the insulation. Such phenomena always give us a phase resolved PD pattern that is very symmetric. We have large phase angle intervals. When I mean phase angle, I mean the phase angle range that is covered by partial discharge activity. We have a mostly triangular shaped pattern, and we have a markedly start before the zero crossing of the voltage. When I speak about zero crossing, I mean when the voltage is zero. So in the PRPD pattern, we are talking about angle equal to 0 or angle equal to 180 degrees. Another kind of delamination is localized between the insulation and the copper bars, the conductor side delamination. In this case, the pattern is characterized by an asymmetry. We have higher negative PD pulses respect to the positive one. We have a quite regular phase angle. There is an imbalance in the magnitude, and the phenomena can start before the zero crossing as well. The very important thing is the asymmetry respect to positive and negative pulses. On the contrary, when we have slot side discharge, so between the insulation and the stator frame, we have very clear positive PD pulse majority respect to the negative PD pulses. We have a quite regular phase angle interval. There is, of course, an unbalanced magnitude, but reversed respect to the conductor side delamination. The PD normally starts before the zero crossing. And one particular thing is that if you look at the PRPD pattern, is it triangular shaped, but we have that the highest PD values, they occur close to the zero crossing and not as a regular triangle in the middle of the phase angle range. Another phenomena we have normally, it's the stress grading discharges. So we are talking about the portion of the generator when the bars come out from the stator core and they have a bending, and we have some stress grading taping to decrease the electrical field. We have normally a higher positive PD respect to the negative PD pulses. We have a quite regular phase angle interval. The shape of the pattern is more rounded compared to what we've seen till now. And they are very, let's say, very easy to find in air-cooled turbo generators, for example. One of the last phenomena is not exactly an insulation defect. We are talking about bar-to-bar and bar-to-ground discharges. They occur in the overhang of the generator between the bars and the pressure finger, or between the two bars. This PD occur in the air, In fact, actually, they belong to the Corona family of PD, and they are characterized by very regular behavior between positive and negative. We have a super high repetition rate of the PD, so we have many of these events each second. Normally, the minimum values of such PD is far from the trigger level. So if you look at the PRPD pattern, there is a gap between the minimum value that we can detect and the minimum value of the PD phenomena. Last, very characteristic squared phase resolved PD pattern. We have normally a couple of square, one negative, one positive, with a 180 degrees phase angle difference, and characterized by rectangular shapes. These were the major PD phenomena and related phase resolved PD pattern. Obviously, when you go on site and you make the test, you can always find a mix of these ones, overlap of these ones, and it's important to carry out a proper data analysis. To carry out a proper data analysis, the first step is to identify and remove the noise occurring in the generator measurement and the eventual face-to-face crosstalks. We will see what are the normal classic rotating machine noise and disturbances issue. We will see in particular the exciter and electronic system noise. Then we will see a solution for such noise like the hardware filtering. And later on, we will introduce the Techimp patent about time frequency map filtering. That is a more customized solution. About the time frequency map filtering, I can tell you that in the plans of the Techimp-Altanova group, there is also another webinar that will be carried out in June or July that is focused on time frequency map only. So if you follow up the dates from the webinar calendar, I guess that in a few weeks there will be also this kind of webinar to participate. So what are the rotating machine noise and disturbances we can have during normal partial discharge testing? We can identify unsynchronized disturbances. Those came from the environment, for example. We have crane excitation, power tool operation, and so on, or synchronized disturbances. What I mean by saying unsynchronized and synchronized disturbances. When I talk about unsynchronized disturbances, that means that there is not a regular correlation with the applied voltage. So, for example, in the phase resolved PD pattern, I won't have triangles, group of points like for the PD phenomena, but I will have flat response of signals all along the phase angle, or sporadic random points here and there. That is the unsynchronized disturbances, and they can cover what I want to see. Instead, when I talk about synchronized disturbances, I mean signal that is correlated with the applied voltage of the generator. That can come from PD source externally to the asset. That can be due poor electrical connection. If we have some floating parts, for example, they can affect the measurement as well. All these kind of things are, let's say, very uncomfortable to be brought inside the acquisition. So if possible, it would be nice to remove them. And in this case, we take advantage of the phase resolved PD pattern to recognize the voltage correlated signal, to identify the PD correlation with their own phases, with the source of the PD, and to identify crosstalk signals. Very classical noise during acquisition is the exciter noise. If you see the pattern here, we have a group of 6 vertical lines, very, very stable and very, very precise. Those are basically covering something else. They are mixed with something else. I can say at first sight that is an exciter noise, and I guess that you can see as well the characteristic of vertical lines. But why it's so clear that is an exciter noise to me? Because normal PD, they are due to the physics. We have an applied voltage that activate and deactivate a defect. So there is a correlation with the phase angle and the change. In this case, these vertical lines, they cover a very, very narrow angle range, and they are very, very regular. Why? Because they are they are clocked. There is a clock on the exciter giving such disturbances, normally from the insulated gas bus transducers of the exciter, and we can find them very often. Very good thing for us, this signal frequency spectrum is normally far from the PD signal frequency spectrum. So we can easily identify them and get rid of them and separate the sources with the, for example, with the TF-map technology that will be explained a few slides ahead of us. Thanks to this time frequency map separation, we can identify properly on the black cluster the exciter noise, on the red cluster the PD phenomena together with the background noise. We can further investigate then this second PRPD pattern. Now, we can use also hardware filter to remove noise or unexpected signals. We can remove low frequency disturbances with the high pass filter. We can remove high frequency disturbances with low pass filters. We can combine these two and get a band pass filter, or we can attenuate the existing signal as well with an attenuator in case we have a very high signal and we need to understand what's going on. Here we have a case with a full acquisition where we have a PD and exciter noise together. If we make this signal just pass through our hardware high pass 2.5 MHz filter, the signal will be more clear. We have lost the frequency component coming, the frequency component belonging to lower than 2.5 MHz, sorry, but we will have all the rest very highlighted. This is very important, in my opinion, if you want to correlate amplitudes. We shall measure the proper amplitudes, not the exciter amplitudes. Then, the main topic for the denoising is a time frequency map. Basically, the time frequency map takes advantage of the information we have in the waveform, in the pulse waveform. Normally, the just two information we got from the pulse is the amplitude and the phase angle, and we create the PRPD pattern with these two parameters. But we can study the same pulse as per its spectrum. We can identify what are the what is the frequency spectrum of the pulse, and we can try to translate this analog information into mathematical numbers. That was the TF-map technology introduced by Techimp. We have one pulse. This pulse will be analyzed on board of the instrument with the pulse amplitude and phase angle. We will build the phase resolve PD pattern, but with the rest of the information, so the waveform shape, we will study, thanks to a fast Fourier transform formula, an equivalent frequency and an equivalent time length. As I told you, it's not this the object of this webinar, but to make it short, with the time frequency map, we are able to see the signal from another point of view, and we can introduce filters and customize filters on this basis. We have a clear example. We have a full PRPD pattern when we cannot recognize any of the patterns seen before, but its TF map signal is characterized by a low frequency signal and a higher frequency signal. We can decide to remove from the acquisition, to customize a TF map filtering just by drag and drop a square over it, and we will get the filtered data related to the PD phenomena. We get rid of what we don't want to include in our acquisition, and we make the PDA signal evident and spotlighted. Now we have seen basically what are the sensors, how we can acquire data, and how we can filter noise. We will see now how we should analyze data. To analyze data, we have to keep in mind a flow of action. First, we have to take into account acquisition parameters. Then we can apply, if we want, some filter with a TF map. And as an output, we will have data set. These all activities carried out during the acquisition. We go back in our office, we go back to our laptop. We can still apply some more time frequency map separation, and we can study the phenomena one by one and trend such phenomena along the time if we have more than one PD measurement campaign for that generator or motor. So the PD analysis actually starts during the acquisition. We have to keep into mind that a very good data set will give us very quick and high quality analysis of the PD. What we should provide to the analysis is high amplitude PD signals data, lower amplitude PD signals data, machine working parameters like load and temperature, as suggested by several standards. We can take information about temperature of the generator and load to make an evaluation of which phenomena are going on together with the PRPD pattern identification. It is also suggested to use different time lengths to acquire the data during the acquisition, different pre-triggers values, and to use hardware filter as well. Whenever I'm doing the trainings to our customer, I always say them that data is free. Once we have everything connected, we have to, let's say, acquire the highest amount of information that we can by changing the acquisition parameters, by changing the filters, and if possible, by taking the measurement in different working condition of the generator or the motor. Here we have the same step. Suppose that we are on site during the acquisition. I can have this information during the acquisition in streaming that we have lower frequency signals and higher frequency signals, and I can acquire the whole data first. So I will have the acquisition on the left saved in my data set. Then I will apply the TF map filter and will acquire the PD pattern present on the right. Both shall be anyways saved in the dataset, because the dataset should include everything: different foot scale, different trigger level, waveform acquisition, presence or not of hardware filters, and presence or not of software filters. When I am back home, I will have, let's say, 20 or 30 or 40 phasosol PD pattern to be analyzed, and I can take this information and use them for my diagnosis. The idea that I always try to bring into the customer mind is that whoever is analyzing the data should be able to recognize each step of the acquisition. So first we have noise and so on, then we start to identify one of the noise, we filter it out, we make a new acquisition. This flux of information should be, let's say, evident to the analyst, not just to the acquisition, not just to the testing engineer. Now we have our data set saved, we are at home studying the data, but we can still take advantage of the time frequency map. Even on the acquired data, we can take clusters from the classification TF map and study the related single sub pattern. And this is very typical in generator, because normally we will have more than one phenomena or crosstalk occurring in the same detection point. We shall be, let's say, good enough in the acquisition to have something to study during the analysis, thanks to the TF map separation. Last point is the identification of the single phenomena. We were able to, let's say, acquire the data properly. We have removed the noise. We have separated the sources. For example, in this picture, we are studying the red cluster signal only. We are marked on the red cluster, and we should be able to identify the phasosol PD pattern. This can be done obviously by a visual identification made by the operator. Our software also provides identification tool that is delicate, is not, let's say, 100% perfect, but if we refine the data properly, it can give us a very good indication. Last, we should study the data along the timeline of the generator. It occurred to me in my career to test generators from the beginning of my career till now, where we are seeing always the same partial discharge phenomena characterized by very same amplitude and very same repetition rate. The phenomena is not evolving. In other cases, we have seen that along in 1 year, the PD phenomena increased and doubled its magnitude and doubled its repetition rate. So it was that kind of information that triggered more the attention respect to a stable high-level PD phenomena. The growth of the PD phenomena means an evolution in the defect that can be very harmful for the asset. Normally, the idea is to use the PD diagnosis of the monitoring. Let's say every 3 months, every 6 months, we have data and we compare the data with the old ones. We try to recognize the same phenomena. In case we see an evolution, we trigger the asset management attention to spotlight on particular phenomena. This can be, let's say, brought into a maintenance action or into a visual inspection to find out what's the issue and if there is a necessity of any maintenance intervention or even rewinding. It was, let's say, the workflow for the analysis. Keep in mind the importance of all these points to separate, to remove the noise, and to check the trend over time. And if I'm not wrong, yes, we have the third question here. Andrei, please.
Correct. Yes, we have the third question, and after listening to this very detailed explanation, how do we try and understand if we have a problem with our rotary machine, we ask you, what is the most consistent parameter to evaluate maintenance action? Is it PD change with temperature? Is it type of PD? Or is it increasing trend of PD amplitude? So which one of these 3 parameters would you isolate to be the most important one, which would basically tell you to stop the generator or a motor and to do some maintenance action? So feel free to cast in your votes. I see already 33% of the people have voted. Also, thank you for the questions you have been posting. I tried to answer some of them. And for some of you guys, I have sent them to our specialist, of course, Lorenzo, who will see which questions, how much time will we have. Hopefully we can answer as much as questions as we can, but take into consideration that you have asked a lot of questions, and I just hope that we will be able to answer at least 50% of them. So after 1 minute, I see 45% of attendees voting, and I see most of you giving a correct result. So let us close the ballots in 5, 4, 3, 2, 1, and the correct answer, of course, is C. The correct answer is C, increasing trend of PD amplitude, and of course 80% of you have answered so is the correct answer, because when the trend of the amplitude rises, so when it goes up, this will be like a signal for you to do maintenance on that particular rotating machine. Thank you for your attention once again, and I give you let's say, I'm asking Lorenzo if he can just now show us the end of the presentation, and we will later have just one more question where we will not have the correct answer, but few answers you can choose just to see how you think and what is most interesting for you. So take it away, Lorenzo.
Thank you, Andrei. Basically, I'm very glad that you have picked up the correct questions, and I've seen some of the questions I will answer in the end. In the last part of this presentation, we will briefly explain what are the solutions that can be put in place by Techimp, or what are the products that can be provided by Techimp for offline testing. For the services, we are talking about offline PD test, online PD test without sensor, sensor installation and commissioning, online PD test with permanent sensor, and data analysis. also remote PD test. Offline PD test is normally performed during outages. It's not our, let's say, preferred solution because of the reasons we have seen in the beginning, but we understand that it's a quite standard requirement, and we can provide this kind of solution. Normally, we do sensitivity check first by injecting a charge into the sensor connected to the winding. Then we make voltage injection and the first readings. We have to wait the standby time to extinguish eventual transient that we always see because it's a very cold machine in this case. And then we complete the reading session with the further measurement and we make our evaluation. Normally, this activity takes 8 hours, I would say one day. In a case of time limitation, we had also to make this test in a very lower time interval, but in this case we are affected by some of the transient that we have at the beginning of the voltage injection. If I can, let's say, put my personal opinion in this case is that sometimes an offline test costs more than a sensor installation and an online test. So, and it's just a once in a lifetime offline test. If I come to your office, to your plant, I test with my equipment, with my sensor, with my acquisition unit, I will get some of the readings, but it will be harder to compare with the next service company. I always prefer at least to have a permanently installed sensor. Our acquisition unit doesn't have any problem with 2 nanofarad, 1 nanofarad capacitive coupler, 80 picofarad as well. We can always take a measurement with all the different sensors and make a comparison in the generator insulation condition. Second solution, online PD test without sensor. Always an outage is required. We install temporarily the sensor and then everything is connected back into position and the generator or the motor is keep running another time. We don't need an external power supply for the voltage because we use the normal line voltage of the rotating machine. We study the normal working condition of the asset, and it's quite inexpensive compared to the sensor installation or the offline test. It's a cheap solution. It's, I mean, I don't sincerely, let's say, suggest this solution. I prefer always to have a permanent sensor installed, but it's something that can be cheaply in one day. Then we have sensor installation and commissioning and recommissioning services. These are our normal activities. We sell the sensor and we offer together with the sensor the installation. We identify the best sensor position. We design eventual installation frames like the green one that you can see in the bottom picture. We study the derivation box, position and cable trunking solution, and we make the installation. Normally it takes 6 to 8 hours from the beginning to the end. And then we have a sensor and signal cable commissioning test to check that everything is okay, the sensitivity is good, there is no mismatch in the phases. That, believe me, it's something that happens, especially with sensor that you don't know who installed. And we also provide services for sensor recommissioning. Let's say that in your facility you already have some sensor. Hopefully we don't have any issues by using this sensor with our equipment, but in order to be sure that everything is made properly, we perform again the sensor commissioning. We check the sensitivity, we check the phasing, and we check the signal cables. Those are normally the weakest point of the installation, especially if the cable is a RG58 compared to RG223 or RF400. This activity is very useful even to make a 0 point and to start a good PD monitoring for the next years, to have a first indication everything is correct and we can go on, and we don't find bad surprises in the future, like taking measurement with the broken sensor or taking measurement with broken signal cables. The very standard service that we provide is an online spot test. We use existing sensor, we have derivation boxes, we connect to our portable acquisition unit, and we take the measurement. It's inexpensive and quick, easy to perform, no outage is required, consistent data trend because now we are using always the same PD sensor, and it's very popular, and it's actually a very good feedback for the asset managers to get information from the generator without big efforts. We also provide data analysis services. We have a customer that, for example, perform on their own the acquisition and they send us the data. We have a customer who have acquisition unit permanently installed and they can download the data from the acquisition unit and send it to us. And we also have a solution with a portable instrument that is basically designed to make good quality PD measurement autonomously without skilled operator. This unit is called Alpha, and it came out of our service department experience, because we have seen that for us it's quite, let's say, easy to take proper PD measurement because it's something that we do every day, but in many cases asset managers perform PD test once every 6 months. So it's hard to keep in mind all the information that we need to perform a good PD test. And with the Alpha instrument, there are few, let's say, several modalities to acquire the data autonomously without any interaction with the operator to get a very good data set to be analyzed. We also provide, especially recently, especially during the COVID time, remote online PD test. So we can use an acquisition unit connected to a laptop that is then connected to a modem or even a routing mobile. And thanks to softwares like Dropbox, we can connect directly from our headquarters and perform the measurement directly. Or another solution is that we have our instrument connected to a 4G modem with a public IP, and we can, thanks to we can make basically a direct connection to the unit itself. Both these two solutions, they have a series of advantages. It's easier for the logistics of the test. It's easier. It's also better for the customer that doesn't want to, let's say, take part of the acquisition, just want to have a very good result with a proper acquisition. And it's thanks to the new technologies, especially with the 4G and the Dropbox and sorry, TeamViewer application. They are very, let's say, comfortable and easy to be put in place. Last chapter. Then we will go to the question and answer section, the Techimp product solution. We have sensor kits, we have acquisition unit, we have software tools, accessories, and permanent monitoring. You can find all the information that you want in our website. I will just briefly list them in the next slide. And especially for generators, we will have, normally we call them motor coupling kit because they are very low voltage, normally characterized by electrical motors, 7 kV rated capacitive couplers, very small sensor. We can sell them normally in 3-phase kit. They come with everything necessary for the installation, so high voltage connection to the bus bar and coaxial cable connection for the permanent installation and derivation box in the end. Same kind of sensor, but for a different application are the PD couplers family for generators. Normally we have identified following the ESC specs 3 voltage level, 12, 17, and 24. They are all characterized by 1 nanofarad capacitance as well as the 7 kV sensor. Let me just point out this. If you have seen in the past that there are, let's say, some OEM that have 2 nanofarad, some OEM like us, they use 1 nanofarad, some of them use 80 picofarad, and these are normally oriented to the acquisition units. Let's say that if I have a certain working principle, it will be better for me to use the 80 picofarad. If they have another bandwidth instrument, it will be okay for me to use the 2 nanofarad. But what with our approach with the time frequency map, there is no more problem on the capacitance. It's not used the sensor as a filter, but is used to get all the information, and then in case filter the information with the TF map or hardware filtering. So our solution is, let's say, more, it's able to work with all of this, and there are not big, let's say, variation. The variation is more relative. If I'm using a 2 nanofarad or 1 nanofarad, I can see a 5% magnitude change. If I use 8 picofarad, such solution will be higher, but I have a different frequency range of the sensor. Anyways, all of these solutions are okay with our acquisition unit, and we can use our sensor accordingly. Then, field testing instrument, acquisition unit. We have two instruments basically right now for field testing, the Aquila and the Micro Aquila. These are operated by technicians and testing engineers. They have both TF map filtering and the selectable acquisition function. We can use them for spot testing and monitoring, but in this case, the Aquila is much more performant. It has a very better performance in the monitoring because it can last days or weeks connected to the acquisition unit and performing sporadic acquisition every 1 hour, 2 hours, and so on. Such function is not included in the Micro Aquila. Here we have some parameters, some specification of the signal of the acquisition unit. You can see our bandwidth is pretty high, 16 kilohertz up to 30 megahertz. We have a 10-bit resolution and a sampling frequency of 100 megasample per second. Both these two instruments are normally sold or offered anyways together with a 3 days training that is part of the service department duty. We normally try to make 2 days in the meeting room and 1 day of practice in the field, possibly. If the field is not available, we can also make something with the PD simulator. That is basically a device to simulate partial discharge phenomena enclosed in a travel bag. PD Pro software tool. We have done recently a webinar about the PD Pro. You can also find all the information on our website, and I think also the presentations as well. PD Pro basically gives us database functions. So we will have the data very organized for each generator, for each motor. We will have data organized also by sensor used and correlated with the time on the trending functions. It includes obviously data acquisition function and PD data analysis tools. So it's let's say it's designed to be used in site for spot measurement. Then the data can be stored in a very ordinate DB, and all the information are at a glance visualized in the system. One note is that if you already have one of our old system and you have data with our old softwares, you can import the data in the new DB. Accessory. For rotating machine, I've identified mainly 3 accessories that can be useful for the customer. The 800 picocoulomb PD calibrator that generates a well-known charge PD signal. It's EAC 60270 compliant. Can be used for sensitivity test to test that everything is going on correctly from the sensor up to the acquisition unit. We also have quadrupole. Those are used with capacitors in order to get proper PD readings. We can customize also such quadrupoles to be used with different sensors. Those are not produced by Techimp. And hardware filters kit. Especially rotating machines, such hardware filters kit are very useful. They can, let's say, give us, they can solve the problems for us of filtering noise in a very easy and efficient way. Testing solution, then the Alpha, the one I was explaining to you. It's a design from this, let's say, from together with the service to get to give the chance to an expert and not skilled operators to make a very good PD measurement. Basically, there is a session of the software that asks to the user the info about the test layout. Are there accessible derivation box? You know the brand of the sensor, and in case of different brands, we have different configuration already set into the instrument. Gives instruction how to connect the instrument to the sensor, like in the picture that you can see here. This is part of the software. Once we have collected all the information, the instrument gives the instruction how to connect the test. Then there is a acquisition data session. It takes a while, obviously, because it's not acquiring just one acquisition, but a series of acquisition with customized solution. And in the end, this data can be sent to Techimp, where our PD analyst will analyze the data and evaluate the hazard, the danger of the PD, and we will give a PD report with the traffic light normally. Now, permanent monitoring system, those are the solutions that he was discussing at the beginning, Andre. Those are systems, those are permanently connected to permanently acquiring data from the sensor. So they are made by sensor acquisition unit and normally by a server. One server can include several monitoring systems from all the generators and motors, and we can also add transformers, switch gears, both GIS that are related switch gears, and transformers. How does it work? Why it's nice to have a Techimp monitoring system? Basically, we don't just take the data, but we have put the same idea, the same philosophy of data analysis also in the monitoring system. We have the analog signal coming from the sensor, PD analog signal. Then the signal enters the acquisition unit. In the acquisition unit, there is already the TF map filtering capabilities, and we can filter out some of the signal that is unwanted. We don't want to save such signal, and save what we want to bring into our SCADA system. The data will be then studied, and let's say there is a process to separate different cluster of points and to identify the single PD phenomena. We provide the single PD phenomena in series, and each one of these PD phenomena can provide an individual alarm phenomena. This is the idea. Obviously, it's very, let's say, just in one slide, it's not so clear, but this is just to share to you what is the philosophy beyond our permanent monitoring system. Use the same advantages we have with online spot testing brought into an automatic system that does not require personnel. We'll just receive individual alarms by email or by SMS, and in case we can check the data and study according to the data. These are the advantages of permanent PD monitoring. We have the asset continuously under working condition. It's a 24/7 PD assessment. We also have, this is something that I've seen that many of the customers appreciate. If we have the acquisition unit for the permanent monitoring, the same acquisition unit can be also used for spot testing with the, let's say, more manual soft, with the PD Pro, for example. We can have individual phenomena trends evaluation thanks to the T-SCADA TF map separation. We have automatic and individual alarms. Can be integrated with other systems, also with the vibration, for example. And of course, the very bad part is that it's a bigger investment for the customer. Now we have the last quiz, and in the meantime, I will check some of the questions and I will answer in the next slide the one that I think that are more important to know. Please, Andre, go ahead.
Okay, thank you, Lorenzo. Now for our last question, as we said, it is not one correct answer. It is just for us to understand what products and services are the most interesting for you. Is it permanently installed sensors, which would enable our service engineer to do a test without stopping the machine? or is it the purchase of acquisition unit so that you can do tests yourself, maybe just the acquisition, or is it a service through an online test, doing an online test, just a pure service, or is it continuous online monitoring? So these are like 4 ways how you can let's say, be more careful, be more focused on your generator or a motor. You can either have permanently installed sensors, or you can have also an acquisition unit, or you can have somebody from Techimp come and does the servicing for you, the measurements for you, or maybe you would like to have a continuous online monitoring system, which would give you a continuous report, what is the state of the insulation on your rotary machine. So I see that you're voting, more than 30% have voted. And as Lorenzo said, after this, we will take some questions, we will read some questions, and then hopefully we will have a satisfying answers to those questions. So I'm going to close in 5, 4, 3, 2, 1, close poll, and let's share the results. So continuous online monitoring usually is the winner. As some would say, it is like the wet dream of every engineer, because of course you can see continuously what is happening with your asset. Also, permanently installed sensors won the second position with 44%, and then purchase of acquisition unit or service had between 37 and 36%. So these are the results, how our public voted. And I'm happy to see so many of you still here. I'm sorry that we are a little bit over 1 hour period, but as we see, there are a lot of new and interesting information to be shared with you. So to close this, I'm going to pass you now on to Lorenzo, and let's see what questions we'll be answering. Lorenzo?
Thank you, Andrei. I'm taking a look at the question. I see that at the beginning of the presentation, there are some doubts about the antennas used for the generator. Such sensors are normally designed just for generators. They can be installed by the generator manufacturer itself inside the stator. They are like stripes. Those are installed along the stator bars. They are not the antenna sensors that you can find for other spot testing. Actually, they are especially designed for generators. Normally, they are installed to get by on any ways under the let's say under the supervision of the OEM of the generators. Then
so sorry, just to be sure, this was the question from Mr. Brandon Verkerk. What antenna type is best for the detection of PD? Okay.
And I would say that we'll also cover, can you explain how the antenna works? Antenna is not, let's say, used for rotative machines, or at least it's not its proper way to be used normally. When we talk about antenna for a generator, we talk about radio frequency antenna installed inside the generator, not from the outside. Then I see what is the value of injected voltage in respect to generator stator voltage. Of course, in this case, since I am a testing engineer, the more information I have, the happier I am. So I would like also to overstress a little bit the insulation of the generator. I want to go 3 times the injected voltage, but if possible, I would like to have 10%, 15% higher than the rated voltage. So suppose that we have a 15 kV rated voltage generator, we have to inject 15 divided by root square of 3 face to ground voltage to have rated voltage. If I can take that value and multiplying such value for 1.1 and inject it, I will be happier. It is a matter of customer service company relation. Normally, such values are agreed together because obviously the owner of the asset doesn't want to overstress the asset. It's not a new asset, it's an existing asset normally. So it's always a matter of discussion between service supplier and owner. Personally, I like to go a little bit over the rated voltage just to have a more clear information. But let's say that in the 60–70% of the cases, the maximum rated voltage that can be applied offline is the the rated voltage of the generator itself. Another question is, can we use a HP source with low frequency as 0.1 Hz to do offline test? Actually, it can be done, but it's not the, let's say that 0.1 Hz is very good with the capacitive loads as cables. In generators, normally you have problems to cover the, to inject such voltage. Normally what is used is a 50-60 Hz generator for high voltage. And also with 0.1 Hz, you cannot, let's say, have the proper phase-resolve PD pattern. 0.1 Hz is used mainly to make localization of PD in a medium voltage cable. It's not, let's say, the appropriate instrument to be used with the rotating machine. Another question, what is your opinion for online PD measurement using RTD? In this case, when I see RTD, I think about the temperature sensor, but from my experience, I've never used such sensor for the PD testing, even because PD phenomena, they are spot problems. They don't give normally a big overheat of the stator. So it's not, let's say, the temperature is not the proper key to look at the PD argument. Then another last that was sent to me from Andrei. When an harmful PD analyzed over time, when, I guess it's when we consider a PD harmful over time. If I have a PD problem that is continuously growing in the 6 months, I would suggest to take some at least inspection and action. If I have one PD doubling its magnitude, for me it's a clear sign of evolution. I understand this question because sometimes during the measurement we can see small fluctuation of the values around 10-15%. Such values can be considered normal due to the test. But if I see a value that is doubled in 6 months, I will take care. Okay, I guess we're already over time. We can maybe close it. I can still remind you that first I will show you our emails and local representative link. I still remind you that even in case you did not get an immediate answer to your question, we will look into the question log and try to answer all of you individually. We have already done it with the previous one, with the previous webinar, and our plan is to doing it also with the Rotative Machine webinar. And I really thank you for your attention. I hope that this presentation has introduced to you to this topic. Of course, 1 hour is not the proper time to have a full understanding of everything, but at least we have fixed some arguments, maybe some information that can be useful for you to, let's say, going deeper into the PD test of generators and motors. Thank you so much, and thank you also to Andrei, that always is always my partner in this webinar and very helpful. And I hope to see you again in the next webinar.
So I also hope that you are more informed, smarter, and be on the lookout for our new webinars. As Lorenzo mentioned, soon he will be doing a webinar on TF map. So for everybody who knows Techimp, the TF map is our essential tool when it comes to separating the different sources of signal, which helps us very much later when understanding what's really happening in our asset. So be sure to subscribe to that. Thank you for your attendance. Thank you, Lorenzo. And it was a pleasure having all you as attendees. We hope to see you again soon, and we wish you the beautiful remainder of the day. Bye-bye.
Thank you. Goodbye.